Let's start today's curriculum by the Po-Yao Chang from National Tsinghua University, Taiwan. And before his curriculum, I will introduce him very briefly. And he graduated from the National Tsinghua University in 2006, and then moved to the University of Illinois at Urbana-Champaign, and from 2009. And eventually, his supervisor was Shinsei Liu. And then after getting the PhD, and he moved to the Rutgers University as a postdoc of Piers Coleman, and then moved to the Max Planck Institute for a while, and then went back to the National Tsinghua University as an assistant professor. And now he's an associate professor at National Tsinghua University. And his research field is topological phases. And today he's going to talk about some aspect in the many-body quantum dynamics. So please start.
Thank you for the nice introduction. So today is a colloquium. So I decided to give a not general perspective, but some very relatively narrow, but with some different aspects on quantum dynamics. It's a very interesting and still rapidly people investigate this quantum dynamics. And I would like to thank my collaborators first. So Xiao Chen and Saran, who was also an alumni in UIUC. So we are really good friend there. And Jed is who I met in Rutgers. Iksu Zhang, who was my postdoc, now he moved to KIT in Germany. And Yining and Henxi is currently my students. Okay, so I just want to give you some very basic motivations. So I'm a condensed matter physicist. So as a condensed matter physicist, we are interested in matters, right? Basis of matter, how we define what is the properties, and then if for more advanced, or if you are more interested in quantum, maybe there's a quantum material aspects for this condensed matter perspective. So, but most of these phases are described in terms of the equilibrium physics, but there's a lot of non-equilibrium physics which are very interesting. And then I think this also gives rise to a huge motivation. But my personal motivation is there's a lot of unknown stuff. And then you don't, for example, if I working on high temperature, Cooper rate, superconductivity, if I work on something, people will say, you are not following this rule, you are not doing this correctly, that you will get strong a critical view from others. But for a non-equilibrium physics, I think the field is relatively in the very early stage. So people are open-minded, you are allowed to make a mistake and you can have your own creativity. So that is my personal, a big motivation to working on this quantum non-equilibrium basis. And then this is just some kind of typical things that can happen for the non-equilibrium quantum physics. For example, you can have a new type of basis of matter that do not have a equilibrium counterparts. For example, there's some transient laser-induced room temperature superconductivities that people can see by shining a laser. Some materials it can have very transient, a high temperature or even room temperature superconductivity. You can have a photon-induced CDW orders. You can have a lot of a dynamic phase transition. So you can define phase transitions in the non-equilibrium kind of a setup. And then people also can investigate some very a basic fundamental physics problems. For example, how do you identify, quantify quantum chaotic behaviors? What is the quantum symbolizations? What is the turbulence, quantum turbulence, for example? And third is more relevant to the experiment. So as what we learned from transport or other a linear response type of theory, we can do some measurements. And then there's a theory explanations by applying, for example, the linear like a response theory, but in principle, for experiments, you can have a large bias. What will happen? Then that will be something relatively hard to solve. So there's still a lot of new developments that I think nowadays experiment is far beyond the theoretical or computational like achievements. And then there's also new type of concept. For example, in open quantum systems, there's a new kind of concept that I just recently knew, that you can have so-called strong like a symmetry, spontaneous symmetry breaking and a weak spontaneous symmetry breaking. There's no counterparts for the closed quantum system. So it's very like a new type of physics. And then of course, you know, there's also like a quantum computing devices. Nowadays, you can do a lot of manipulation, measurements, quantum controls to design a state. So it's a new kind of directions for us to investigate. Okay, so this is the motivation. So the plan today is I want to, first of all, just trying to convince you quantum entanglement can be a very useful tool to understand this non-equilibrium physics. So I will first showing that we can understand what is thermalization, and then I will first introduce why thermalization is interesting. So it's very generic properties of a quantum system. And then I will show two type of a very like a specific model about strong correlated system, why quantum dynamics can give rise to some interesting properties. And the last thing I will talk about is purely like you can understand some or engineer some type of a non-equilibrium basis of matter by using purely the algebraic structures. Okay, so this is my plan today. So you can see it's very narrow, but there's some interesting perspective. So that's also designed for my title. Okay, so first is how do you measure quantum entanglement? So it's very elementary. So I believe all the audience know you define the entanglement from doing the bipartition. So we are consider entanglement. So it's will refer to a quantum system. So you have a state, you can define a density matrix, you do partial trace, and then you can use this reduced density matrix to measure or characterize entanglement. So a typical example is, for example, this is so-called the entangled state. You cannot separate the A and the B by in terms of product form. For this one, you can design, you can construct the density matrix, and then you can construct the reduced density matrix rho A. And of course, then you can do the entanglement measurements. For example, this is so-called the entanglement measure entropy, and it gets you the non-zero value, indicates this state is entangled. So this is very simple quantum state. This all people all know, but this also can be computed easily. But on the other hand, for a condensed matter perspective, we are interested in many body basis of matter. So in principle, I can have a very like a complicated wave functions. I can still use this definition to compute, but it can be a very hard or very expensive calculations to do this quantum entanglement measurement. So then you need to ask why you are interested in this quantity, why you want to compute this one, right? If it's very expensive. So the reason why people are interested in entanglement is people realize, at least in terms of a condensed matter perspective, it can give a quantity that we can distinguish different bases of matter. That's what's one of the motivations for condensed matter physicists. And then, of course, there's a way you can have a more refined structures to understand basis of matters, right? Okay, so this is some of the motivation, even though it's very hard to compute. Okay, so one of the idea, for example, is this like a so-called entanglement Hamiltonian. So let's suppose you have a reduced density matrix construct by a single pure ground state, so the pure state, and then you do partial trace. However, you can define this entanglement Hamiltonian. Consider the effective temperature in subsystem is like a beta equals to 1. And then you can analyze the spectrum from this reduced density matrix. And then people realize, even though this reduced density matrix is constructed by the ground state. This entanglement Hamiltonian contains all the excitation. So it's very like an interesting like a concept. Ground state do carry a lot of informations of the subsystem, even though it's just a ground state, right? Because typically you will think ground state is orthogonal to other excitations. So ground state has no access to other excitation, but this is an example showing ground state do carries information about the other excitations. So now you can see this is very powerful. And then later I will show you about this entanglement Hamiltonian, the spectrum of the entanglement Hamiltonian. Okay. On the other hand, just for what I told you, like the very like a typical entanglement measurement, so-called the entanglement entropy, this quantity itself can also distinguish phases of matter. For example, 1D critical system has this logarithmic scaling, D-dimensional Fermi liquid with additional L in front. And then for the gap system, you get this area low. So you just compute entanglement entropy for a ground state of a given Hamiltonian, and then you can distinguish phases of matter. So it suggests entanglement can be a very powerful tool to classify, diagnose the system. And then there's other more different types of entanglement that people are investigating, for example, negativity, mutual invocation, etc. Okay, so now I want to change the gear. So I first introduce entanglement as a tool, and what I want to study is the summarization. So why summarization is interesting, then I will try to explain to you. So first, I will just interchange summarization and ergodicity. So as you know, ergodicity or summarization meaning when I drop ink on a glass of water and eventually it's spread into the entire glasses, right? So it's like a thermalized. So what is a very interesting phenomenon. Why is that? Because no matter which drop you put inside this water, it eventually will go to this configuration, right? So it's like a initial state insensitive kind of process, right? So you can realize this kind of summarization also have a similar property present by if you have a box with coin, this is Taiwanese coin, and then no matter what kind of initial state you put in, you shake the box many times, it will basically have a configuration with half head and half tails, right? So it's like a ergodicity theorem saying that the random process basically average over the time period is equivalent to average over the space, the phase space. Okay, but in quantum system, this is not easy to understand. Why is that? Because in quantum system, we know, at least for closed quantum system, everything is deterministic, meaning for different initial states, when they evolve, they should evolve to different states, principle, and then we know how it's evolved because it's purely governed by this unitary dynamics. So it's very different than the previous setting that the process is initial state independent. This seems suggests like for any given closed quantum system, the state evolution is initial state sensitive, right? So summarization is hard to imagine in quantum system because it's deterministic. However, for physics, what we can do is not really see the states. We are seeing the observable quantity. For a given local observable quantity, it suggests it's initial state insensitive. So it's somehow like a summarization, like an initial state insensitive. So why is that? It's still an open problem, but there's a hypothesis why this kind of local observable quantity looks like a thermal process, right? So it's called the eigenstate summarization hypothesis. So their explanation is the following. So there are some for example, I consider a state evolution using this spectral decomposition, and then any observable quantity, like for a long time, the off-diagonal parts for different eigenstates, basically because of this dissipation, they vanish to zero. The only left is the diagonal parts element of this observable quantity, and then they are all equal. So it's very much like a microcanonical ensemble suggests it's a thermal state. So it's like a way that people try to conjecture why a quantum state can be thermalized. Okay, so it's a kind of so-called eigenstate thermalization hypothesis. But I'm interested in more like a strong condition. So this just saying the off-cycle part vanished, and then the local observable quantity looks like a thermal state, thermal excitation value. But for a stronger statement, it's saying that since O is a local observable quantity, so the subsystem reduced density matrix, if I O, the expectation value is like the thermal expectation value, that indicates the reduced density matrix should like a thermal density matrix. So it's a stronger versions of the ETH. So if the reduced density matrix behave like thermal density matrix, as we know, entropy is extensive quantity. So that will indicate the entanglement entropy must satisfy the volume law. Okay, so now you can use this volume law or not volume law to understand or to diagonal to classify the states can be thermalized or not. So for a thermal state, the entanglement entropy will be a volume law. For non-thermal state, for example, many body localized state, it will violate the volume law. And then you can do some dynamics for the system. For example, I consider a system starting with some kind of a non-entangled product state, and then I hammer it by doing some quantum quench described by some Hamiltonian, which is a very generic Hamiltonian. So if the system can thermalize, that indicates the entanglement start generated, so it will increase, and then it saturates to a value which satisfies the volume law. On the other hand, for the system which cannot be thermalized, for example, the Hamiltonian is described by some kind of many-body localized Hamiltonian, and then you somehow do a sudden quench by this many-body localized Hamiltonian. It will not grow, it just go into some kind of area law behavior, and then there can be some transitions between the localized many-body non-thermal localized state to the thermal state. Okay, and then this can be understood at least in terms of this entanglement spread in pictures. Okay, so that can be one key motivation showing that entanglement can be a useful tool to understand thermalization. Okay, and then this has already been studied and even demonstrated in experiment. Okay, so this is a cold atom experiment by Brenner. So what they do is they have a two copies of cold atoms on an optical lattice. So these are two identical copies. They can have a fine tune of interactions from this MO physics. And what they do is this MO physics basically is a Bose-Hubbard model. So they can doing a certain change of parameter goes from a Hubbard gapped state to a superfluid state. Okay, so from an insulating state to a superfluid state, and then see how this entanglement is spreading. So experimentally, you can measure the entanglement in the system from parallel. So that's what they do. So they have two identical system, and then they do certain quench, and then they do some measurements of quantum interference, seeing the second rank entropy, and then for subsystem A, they see something like this one. If subsystem is 2, something like this one, linear growth and saturate. So 3, linear growth, saturate. And you can see this basically is proportional to the size of the subsystem. And 6, of course, there's nothing because there's 0. And you can see this basically showing this system can thermalize because it's satisfied volume law and the entanglement spreading is linear. But it's still very surprising because it's hard, at least for me, it's very surprising. Just 6 atoms, you can have thermalization process. So for any classical system, if you have 6 particles in the box, you tell me they can thermalize. I think it's hard to imagine what is the configuration of thermalization, what is the ensemble meaning here. But for a quantum system, you know, if for 6 atoms, it can be a tremendous large of degrees of freedom. So quantum system is very special. Even 6 atoms, they can thermalize by themselves. So So in terms of entanglement entropies, properties, people already know. So what I want to know is there a more like universal way, a universal properties for state approach simulations? So in terms in the perspective of entanglement. So that's what we are studying this paper. To investigate this kind of a simulation transient time process, what we do is this by two types of kind of a setup. One is so-called the random circuit model. So this model is very like easy to numerically do, and then it also represents generic quantum dynamics. For example, and why it's easy, because you consider some given product state or given initial state, you just sequentially drive in by some two-side unitary gate along this time direction with this kind of a period structures. And this kind of evolution, people already demonstrate it can basically has the same property as you consider a state evolved by a generic Hamiltonian. For example, this is a very typical Hamiltonian. So it's a Ising model with transverse and longitudinal field. So it breaks basically Z2 symmetries, can be a very chaotic Hamiltonian. So these two properties I will show, they basically share the same simulation process. So how we are doing this is we create some initial states. We let it evolve either by this random unitary circuit or this generic Hamiltonian. And then we do partial trace. We want to monitor the spectrum of the entanglement entropy and then see how it's evolved to the thermal state. And then we find there's universal properties of this entanglement spectrums as a function of time. So to understand this, first I want to show, introduce you to another thing to understand all this entanglement spectrum, because I'm using the level statistic to understand the entanglement spectrum. So why level statistics is important? Because for a given thermal state, we are trying to consider ergodicity process. It will go into a chaotic system. And then, as you know, this quantum chaos or for generic chaos type of or an integrable property, you can use the level statistic to understand their property. For example, if the system has a lot of conserved quantities, you know the level can cross to each other because of conserved quantity. So there's no level repulsion. On the other hand, for the system without conserved quantity, it can be very chaotic. The different state can basically exchange energies and momentum, for example, angular momentum. So they have level repulsion. So the idea is basically that from Wigner that you can describe these chaotic behaviors by this random matrix series. So random matrix satisfy some generic kind of a level statistic in terms of their symmetry. For example, for GOE, you have this kind of symmetry with time reversal symmetry. And if the system is integrable for example, for this kind of a rounded circular shape of boundary condition, it's integrable. You have lots of conserved symmetries. So basically follow this Poisson. So you can use this level statistic to understand quantum pairs, or the system can be thermalized or not. Okay, so we are trying to use this level statistic of the entanglement spectrum to understand the system is thermalized or not. And then the typical way you compute is using so-called adjacent gap ratios of spectral form factor. But this is very technical. I will not explain too much, but that's basically is an easier way to know it's either Poisson or the GOE or GUE statistics. Okay, so first of all, what is the entanglement spectrums when you do the sudden quench, or this evolved by random circuit or by Hamiltonian dynamics? So what you first see is you start with the initial states, the product states, no entanglement at all. Once you quench the entanglement spectrum, basically the eigenvalues of this minus log rho A spread out. So you have an increase of your bandwidth in the entanglement spectrum, and then it suddenly shrink. However, this shrink will not be seen if you consider the entanglement entropy still grows in. So why this gets linear increase and then shrink because there's a light cone. So in this typical example, I'm consider the subsystem size is 8. So once you do a sudden change of parameters or drive by some random circuits, you start develop quasi-particle. So it takes 4 time units to traverse the subsystem. And then now it knows it's hit the entanglement boundary. So the entanglement bandwidth will not get expand out. So this is a light cone figure that is not seen in the evolutions of the entanglement entropy. So this is something very generic. You can see the same for the random circuits or for the Hamiltonian dynamics. On the other hand, there's distributions of your eigenvalues of the reduced density matrix before hitting the transition. Basically, they are scale-free like a distribution, so they don't feel any scales, okay, because they don't feel any boundaries at all. So there's a very like a specific time features for this dynamics. Third one is like what I told you about the level statistic, which can characterize the GOE or G. Here is the GUE level statistic, where there's a level repulsion corresponds to the system can be thermalized or the non-entangled like a Poisson state. So at like a order 1 time, it starts develop the level statistic. So if the R value, which is the adjacent gap ratio defined in this way, so I will not go into detail, then it indicates there's a level repulsion, but this level repulsion only comes from the nearest level repulsion. But basically, it suggests that when I consider a thermalization process in the order 1 time period, the system, the nearby level starts have level repulsion. They exchange energies, and they will start thermalize order 1 time. On the other hand, I can also compute the global one, the global level statistic. Global level statistic. And you see people, there's, I will also not go into, but this is the formula. So basically this compute all the levels correlations for difference. E is the entanglement spectrum's eigenvalue. So it's basically a way to measure the level between all the global level correlations. And if there's a RAM plateau picture, meaning there's a level repulsion. Okay, so you can see at early time, it start develop level repulsion, but it's only collapsed to the same curve at a very late time. So the system eventually thermalizes at that time, where also indicate entanglement entropy saturate to a volume low value. Okay, so now we can conclude the thermalization process for a generic Hamiltonian, closed Hamiltonian system. Basically have 3 universal time scale. One is the order 1 time scale, where the reduced density matrix eigenvalues distribution is scale free, and then there's a nearest neighbor level repulsion developed at order 1. The second time scale is depending on how you bipartite your system. There's the light cone structures characterize this time scale, and third time scale is it's eventually thermalized, where the entanglement entropy saturates to a volume low value property. So this is just the first part about the aspect of quantum thermalization. Now I want to change the gear to the correlated physics, the quantum dynamics. So it's very specific model, so not like the generic quantum dynamic I described before, but these models are interested by themselves. For example, Condon model is one of the things I will talk about today. Why it's interesting? Because people back in 1935, 36 here, you can see there's a increase of resistivity when you're lowering the temperature for metals with dilute magnetic impurity. So this was a puzzle for people why the resistivity will increase when you lower the temperature, and basically Kondo solved by this Kondo Hamiltonian. So they consider some Heisenberg type of interaction between the impurity spin and the electrons in the metals. So the idea is there's a simple way to understand it by considering when you lowering the temperature, the electrons for conduction. So red line becomes some kind of a lead for a metal with electrons. This is some magnetic impurity. At low temperature, they form some singlet state. And once you form the singlet state, there's a bound state. So they can have a phase shift for other plane wave that's hitting this boundary, right? So if the boundary condition give you a pi half shift, then you can have a destructive like a interference in terms of transport. So if you do the transport calculation, for example, by computing the transmission metrics, then you can get zero conductivity, for example. So this is a simple way to understand why you can have an increase of resistivity due to the formation of this bound state. So this is a very interesting correlative physics. Okay. So people can understand from the boundary state condition. Then there's a more bizarre or more like a bizarre like a variance of the Kondo system is so-called multi-channel impurity models. So of course there's a different perspective, but I'm only focused on one single impurity. So I'm consider people are interested in this problem because this multi-channel Kondo impurity shows non-Fermi liquid property, and then there's some anions in this system, the fractionalizations of some electrons. But I just give you, and described by this Hamiltonian, but I just give you some pictorial understanding of this model. So I have a very big spin, so it can be has some SUN representations, okay? And then I have different channels of conductors, conduction electrons. So I have a very big N spin, and then couples with K channels of conduction electrons, and then they have Kondo interactions written here. So this can have non-Fermi liquid property. And then why it's non-Fermi liquid? Because unlike the previous case where they form the singlet, now the electron, K-channel electron, cannot perfectly screen this SUN spin forming a singlet. They can have this multiple kind of a particle and whole kind of scattering process. So you can, for example, you have a electron scattered by this impurity with 2 electron back, 1 hole inside, and 3, 2, for example, with different amplitude. So this can be a very bizarre dressed state which has no good quasi-particle description. And if this is the case, then we will say this is a non-Fermi liquid system. Okay. And then people also find this can be interesting. For example, if you consider 2 channel, just like a 2 different spin coupled to a 2 different leads coupled to a spin, or 3 different leads coupled to a spin. If you measure the local impurity entropy, you get this irrational number. So it indicates the internal degrees of freedoms in the spin gets fractionalized. So it's kind of an anion. So 2 channel, believe it's a Majorana fermions, and then 3 channel is a Fibonacci anion. So there's a way that people can understand this fractionalization of this multi-channel Kondo impurity model. Okay, so from the equilibrium setting, it's already interesting by itself. But what I'm trying to do is I want to do a sudden change of Kondo coupling and then see what's the dynamics of this system. Okay, why I'm interested in this? Because people study the so-called SYK model, and SYK model is a non-Fermi liquid model. And then people showing this SYK model, which characterized by random 4 Majorana interacting Hamiltonian in 0 dimension. And then people can map this to black hole, etc. But in terms of non-Fermi liquidness, basically showing there's a power law singularity in the Green's function. It happens the same for the multi-channel Kondo impurity model. So there's a similarity between the SYK model and the multi-channel Kondo impurity model. And then for this multi-channel Kondo impurity model is a physical model that people can do experiment, and then they can have some physical observable quantity in terms of this non-Fermi liquidness. For example, the heat capacities can have this kind of power law property terms. And back to this SYK model, people use this level statistics showing it's a quantum chaotic system. So my motivation is I want to know this multi-channel Kondo impurity model is very similar to SYK model. Is it a quantum chaotic system or not? Okay, so this is my motivation. But before doing things, this already been solved by various techniques. For example, boundary conformal field theory, beta ansatz, large n, etc., and even numerics. But if you read these terms, you know this indicates this system is integrable, so it cannot be chaotic. So there's some kind of a thing that I'm very curious about non-Fermi liquidity similarity to SYK model and the integrability. So what is the dynamic of this system? So this is the motivation for us. So we'll not go to the detail, but what we are doing is using the large n field theory to solve this problem and using the KL division. Okay, so this slide is designed to skip. So sorry for that. Okay. So what we are doing is computing a sudden change of the Kondo coupling. So it can be greater than the pre-quenched J or be smaller than the pre-quenched J. J is the Kondo coupling. And then we can measure the impurity spin correlation function. Basically, it's decays, but it can have different decay rates, depends on the initial state. And then we can also measure the so-called, we define a Kondo order parameter, basically the impurity spin dots the conduction spin on top of this impurity spin. And then we see how the time profile of this order parameter. So this can be an oscillating function and it saturates, it indicates thermalized, for example. But interesting thing is we can also extract the temperature if the system eventually thermalized for a day, because we can compute the spectral function and extract the temperature from the spectral function. But we have two objects for the spectral function. One is the F fermion. The technical calculation is we trying to use the abricosal fermion representation for the SUN spin. So we have a fermions corresponding to this spin. So we can compute the temperature once it's equilibrate corresponds to this F fermion's temperature. On the other hand, we can also have a composite boson where the F fermion combined with the conduction electrons. We define the phi. We can also extract the temperature for this object. So we can have two temperatures. So it's interesting to know, does this two temperature goes to the same temperature when it's equilibrate? Okay, so this is our result. So this corresponds to the temperature for the initial state. So we can have the temperature which below the Kondo temperature indicated non-Fermi liquid state, or the temperature is high, which is the Fermi liquid state. And then we do a sudden changes of the Kondo coupling, which is less than initial or greater than initial. So what you see is the temperature doesn't go to the same temperature once it's equilibrated. So it's something very weird. So we call it quasi-equilibrium. And then the other thing is we see if we increase the Kondo temperature for the post-quench Hamiltonian, basically you see the temperature basically decrease. So it's like a cooling. But you can understand this cooling because you are reducing the configuration by strengthening the Kondo coupling. So you can have a way to cooling the system by just doing this sudden quench. So this is what we observed. And then of course, we can also ask about, for example, the quantity. For example, this is the saturation of the order parameter indicates is thermalized. And you can see they thermalize very quick, like a transient time. Although they didn't equilibrate to the same temperature. However, there's a different properties for this dynamics. So one has this oscillation, the other is not. It depends on the initial state. So if the initial state starts with this like a non-Fermi liquid state, it's indicated the initial state is very entangled. So once you do a quench, it has this kind of oscillation. On the other hand, if for the high temperature Fermi liquid state, the order parameter, they did not form any entangled state between the impurity and the conduction, and then you don't see these oscillations. So you can see the dynamics strongly depends on the initial state. So there's also some fine structures that I will not tell in details, but this is some aspect. But actually, this is something that we are trying. We did, and then we find it's interesting. But eventually, we did not confirm it's a chaotic system or not. But there's something that we think it's more like an integrable. But you can see this quasi-equilibrium because they didn't like the equilibrate to the same temperature. But this is an artifact because it's a large N treatment. So we don't consider any feedback effect to the conduction electrons. So if you consider 1 over N, it will the correction, it will eventually thermalize. Okay, so this is what our conclusion. Okay, the other thing is another model that's draw my attention because this is so-called the hot sky homoto model. It's a Hubbard model. So you can see this is bilinear fermion. It's like a regular band, non-interacting band theory for the free fermions with some orbital degrees of freedom characterized by alpha. But if you put the interaction, you put it in the momentum space. So the interaction Hubbard U is in the momentum space. So why this is interesting? Because this model, even for a single orbital case, it can show some non-Fermion liquid property, and it's exactly solvable because it's expressed in terms of but the interaction is expressed in the momentum space. Okay, but this model has been revisited recently because now you can put some topological flavor in the bands, and then people are interested in how does the interaction in the momentum space that change the topologies of bands. Okay, the free fermion. So it's now draws a huge attention recently, and then you can have a interesting perspective because if you express these interactions in the real space, it's become highly non-local. So now you can ask about the non-local. How does this non-local interaction give rise to a new physics? So this is some aspect why there's a revisit of this HK model. But my perspective is, if you look at this real space representation, I have bilinear fermion, quartic fermion with this long range interaction, and then I consider random Hubbard U and then random hopping. And then you compare to the SYK2 plus SYK4 model, they are very similar. And in this model, people investigate the transition between chaotic, where the SYK2 is not present, to a integrable system where the quartic term is not present. Okay, so this is very similar. So I just wondering, can this also show this kind of an integrable to chaotic transition? So just doing something that may be interested and trying to see. And this is the result. So because of numerical reason, we can only do finite number of orbital number in this model. So this is 2, 4, 6, 8 in terms of orbital number. And this is the variance of the U, and this is the variance, the Hopping. And I'm computing so the previous, the adjacent gap ratio. So the yellow one will become chaotic, and the light blue one is the integrable. So if you see for the large orbital, if you have some finite variance of U, it can transit from an integrable model to a chaotic model. And same can be seen for this spectral form vector. So this is computed for I think this is 6, this is 8. And you can see the solid curve corresponds to the computation directly from the random matrix theory. So basically they line together at some values for the orbital is large. So we expect that for a large orbital size, it will be identical to the random matrix. So there's a transition in this model as well.
Can I ask a question?
Yes.
So what is U?
U is the variance
of
of the interactions in field.
Yeah. What is a function of U?
The function of
Gaussian
function.
Yeah,
Gaussian function. I randomly choose a Gaussian function. And then the average U is 0. Sorry.
You mean it not some constant function?
Constant,
the-
yes, it's a constant. Sorry, it's
I mean some
zero.
function, but you
I randomly choose the U. So there's a complete. It's an ensemble of U. I consider
Mm.
disordered system.
then you okay,
I have a
to-
Gaussian profile of U, and then I randomly choose a U in this Gaussian distribution, and then I compute the.
what do you mean? So you is a function of K. So what do you mean randomly choose?
Oh, sorry. Okay, so now this is so different K. I choose different Gaussian function, a value of inside the Gaussian distribution.
Okay, I see.
So different K, I have a different realization of this interaction, but everything is random. Yes. Yes. Breaks the integrability. I think so. I think there's no integrable. If there's a U, there's no integrability. Yeah. Yeah. Because K is good. Yes. Yes. Yeah. So it's not integrable. You mean the previous like a multi-channel condo impurity model? Yeah. So the idea is the following. So people use the boundary conformal field theory in terms of very low temperature. So low temperature, there's a there you can really think everything still have a conformal field, conformal symmetries with boundaries. And then the impurity just change the boundary conditions. Yes, but for general case, I need to vary the temperature. So above some temperature, the boundary conformal theory is not reliable. Yeah. I think maybe, yeah, but it's not exactly the same because the SYK is like a zero dimension object. So in here, if I want to think this multi-channel condom impurity model as a zero dimensional object, first what I'm doing is we integrate out all the conduction electrons. So there's a induced like a SYK like a particle in the F fermion terms. So but there's no randomness in here, so it's different than the SYK. The coupled like Green's functions is very similar to the SYK model, but it's not exactly the same. So the structure is slightly different, but they all shows this power law singularity when you solve the Green's function. So the last thing I will talk is just considering the algebra structure. So it's very general in terms of algebra, but I not general in the sense I'm considering only the SU11 algebra in here. So now I'm not referring to any specific Hamiltonian, I'm just consider algebraic perspective. I have 3 sets of SU11 generator by K, and then I consider define a unitary operator by this combination. And then I want to ask how this states evolve by how the entanglement properties evolve by these unitaries has different kind of classification depends on the parameter A plus A minus A0. So this is the setup. So to make it more solvable, we consider starting at some kind of coherent state, because as you know, this is just like a ladder operator. So you can consider a generalized coherent state construct by this ladder operator. So if you look at this formula, I can think U act on this coherent state as some displacement operators with some parameter C with depends on A plus A minus A0. Just for completeness, I write this function, but it's just like a displacement operator acting on your coherent state. Okay, so just change the shape of your coherent state. And then you just ask about the dynamics or physical quantities of this measured by this coherent state. Okay, so it's purely like a general. And the good thing is the physical observable quantity can be expressed in terms of the expectation values of this K0, K1, K2. And then they can be using this complex Z to as a parameters for this observable quantity. So what I'm saying is the observable quantity will only depends on the expectation values of K0, K1, and K2. And this K0, K1, and K2 only depends on the parameters that I put in my U here. So it's very general setup. Okay. So then since this is very general, then we can ask about how this parameter Z evolve under this parameter space, right? And then this basically can be, so Z is defined on a Poincare disk, which is a unit disk. And then we can consider this SU11 as a Mobius transformation of this coordinate Z to another Z plane in here. So we can ask about the trajectories of this Z acts by this unitary or act by this M. So it's the question will translate to the trajectory or dynamics of a state governed by these SU11 generators. Now it's translated to trajectories on a Poincare disk by this Mobius transformation. So these people already know there's 3 types of trajectories act by the Mobius transformation on a Poincare disk. One is elliptic case, which is periodic in green. So that's indicate there's a 2 fixed points for these functions, one inside and inside the disk, the other is outside, so it's circles. The other one is the one where the fixed point is exactly on the boundary, so it's just flow to the boundary. So it's hyperbolic path. And the other one is in between, so it's asymptotically approach to the boundary, hyperbolic path. So now it's the question, the property now we know. So for this quantum dynamics governed by the SU1 generator, we'll only have these 3 different classes. And I want to show why is this really relevant to physics? The answer is yes, because we can apply to several interesting physics that can be expressed in terms of this SU11 generator. So one is this interacting bosons. So this is interaction of the boson. So C is the boson creation operator. Okay. So U I can change to attractive interaction, so they will be BEC become Bose-Einstein condensate. So so experimentally you can put bosons on an ion trap, on a harmonic trap, and then you tune the interaction by some Feshbach resonance, and then they can suddenly become attractive and become BEC, and then you change the parameter of U, making the attractive interaction stronger or weaker, and then see what happens. And people measure this, and then they see the first demonstration, you see there's a recurrence of the quantum state. So it's like one of the coherence that like the coherence state is like the oscillator. So it will like recurs back to its initial state. So this people can demonstrate. But there's other possibility, like I show you, for the thing that can recurs back to itself like a circular orbit, like the previous, on the Poincare disk. Okay. Anyway, this model in the low density sector, basically you can do some mean field, and then it can be expressed everything in terms of this SU11 generators, and then you can start with some condensed initial state with 0 momentum, and then you just trying to drive by this Hamiltonian and then ask what will happen. So just like I told you, there's 3 possibility. One is there's a recurrence of the BEC. The other one is basically you increase, it starts increasing the particle number. So this is the entanglement entropy, but the particle number will increase. In the case, the BEC will get destroyed, starting heating up. So it's called a stable recursion, like a recursion state, or the unstable, like a breaking of the BEC state. And there's a transition between. And then you can also compute the entanglement entropy. So the entanglement entropy for this BEC, I'm doing bipartite in the momentum space K, and entanglement between K and k. And there's a linear logarithmic t, and then the transition, and then this oscillation functions. So it's a thing that can be understood just from the, so this is experimental thing, but you can understand from this algebraic perspective. And there's also other interesting thing. For example, this also can be experimentally engineered. So I'm consider two quantum harmonic oscillator and couple them by this Q1, Q2 at t from t0 to t equal to capital T1, and then I detach this, decouple this quantum harmonic chains between T0 and T1. And then I sequentially doing this, so it's like a flow K. And then, of course, these quantum harmonic oscillators can be engineered, experiment, and can control everything. And then now I want to show you it also can be expressed in terms of this SU11 generator. But now I have two sets of SU1 generators, so it's become more bizarre. But as you know, there's a heating corresponds to the amplitude become larger and larger for this coupled quantum harmonic oscillator, or they just a recursion effect. So in terms of the entanglement, this is an entanglement negativity, but just linear in T. I can also compute it for the heating phase, and then non-heating phase. Basically, it's an oscillating function, and this is transition, for example. However, there's a more like a fine structures, because now I have two sets of SU11 generators, indicate I have a two Poincare disk. So there's one possibility this the trajectory on for both Poincare disks going to the boundary, or the other one is going to the boundary, but one is going to the boundary, but the other one is just becomes like a closed orbit inside the Poincare boundary. So there's two possible scenarios that can be characterized as a heating phase, because if one of the Poincare disks going to the boundary, it will be heating. So now this is something that we want to know in terms of the entanglement entropy slope. So they are all increased linear in time, but the slope is different. So we can expect if the two Poincare disks goes to the boundaries in the same as a same like a form, they will have a larger increase of the entanglement entropy. But if only one Poincare is going to the trajectory going to the boundary, the other one is doing the circulation, then the heating slope should be smaller. So we want to do this measurement, slope calculations. So this is plotting along this line. So the blue one corresponds to only one Poincare disk get hit, but the yellow one is two Poincare disks get hit. So you can see the slope is smaller, but there's a sudden jump when it hits the yellow region and goes back to the green region, which only one Poincare disk get hit. However, if you measure the phonon numbers, phonon population, which is another observable quantity, it grows exponentially, so we take log. So the exponential profile is still a smooth function. So it indicates entanglement still presents as a more powerful tool to see this transition. This phonon population number is still like insensitive to seeing this boundary. So this is one thing that we find is interesting. So this is just a two Poincare disk. So it's give more flavors compared to the previous study, like only one Poincare disk. Okay. So now I would like to conclude my talk. Okay. So first, I want to show this general property of the summarization. Second, I show there's two different specific models which I find interesting. There's some integrable, non-integrable transition, and then also the quantum dynamics. And then there's a lot of development still required. And then the third one is the algebraic, just purely using the algebraic structures to design or to understand some kind of physics, for example, the BEC setup. And then, of course, there's some extension. For example, this is just SU11. In principle, we can ask about if there's a more interesting kind of compact group structure that give you different bases of numbers. And then, of course, the boundary CFT approach for this problem also. Okay, thank you very much.
Thank you very much. So, is there any questions?
So you said the simple spin quantum Ising model in the magnetic field and the random circuit behaves quite similarly under thermalization process. But then this is kind of surprising because one system is completely regular and non-random, but then the other system is completely random. So I think this is maybe my guess is that this is because your Hamiltonian doesn't have any obvious symmetry. That's why they behave similarly. Am I right?
Yeah. So, but so I did not. So for the random circuit model, we can also consider the symmetries as well. So we can consider, for example, the local Hilbert space for each side can be 5 or 6, but we can consider more symmetries. And then we do this in our paper, so we basically see the same properties. So if you add in some finite number of conserved quantity, the dynamics still very similar. Yeah, even for random circuit, but you cannot make it integrable. Just put some little amount of conserved.
So do you think then this kind of coincidence or this similar behavior is universal?
Yeah, at least people investigate. For example, they can see this propagation of the front of the entanglement, etc. They basically has the same property as the Hamiltonian dynamics. So it's quite in terms of general property, I think they share something.
Thank you.
More questions?
No, thank you. I have the same similar question to the first topic.
Okay.
You mentioned that the free rate oscillation emerges if we start from the non-Fermi liquid state.
Yeah.
So
yes.
Yeah, it might be very surprising. So are there any intuitive expression for such a oscillation occurs?
So this oscillation period is in the time domain, right? And then we find this oscillation period only depends on the cutoff of the conduction electrons. So when we do this calculation, we need to integrate the conduction electrons. So we have a cutoff of the conduction electrons. And the oscillation period is depend on the inverse of the cutoff of the conduction electron. So it's really like a Friedel oscillation where you have a KF, right? The KF is where you put the Fermi level, and then the Friedel oscillations in the space is inverse of the KF.
So why it occurs only in non-equilibriums?
But no. So I'm just saying this is in the time domain. So in the real space, you do have a oscillations of your wave function profile, which depends on the cutoff where your Fermi level. So you have a Fermi level. But in here we have a cutoff in terms of energy because I'm considered time domain.
Oh, okay.
So it's in terms of the similarity.
Yeah, and this graph shows maybe S dot small s. Yes. So what kind of measurement can we observe this kind of?
Yeah, that's
so what kind of observable to?
Yeah, so we call it a local order parameter, but in terms of measurement on the maybe I don't know. I think maybe there can be a way to use spin polarized STM, for example, and then have a time resolved spin polarized STM, measure it directly on top of the magnetic impurity, but together with the conduction, it will be big S plus a small s, not as small.
Yeah, yeah, I thought that it might be interesting if we can
Yeah,
see
yeah,
this kind.
I
Yeah. So thank you.
Other questions? So if not, let's start speak again.
Thank you very much. Yeah, thank you. Yeah.